My friends, I want to speak to you today about something that has disturbed the foundations of physics for more than a century. Something that, when I was a young man sitting in the libraries of Paris, reading the works of Einstein, of Planck, of Lorentz, troubled me deeply. Not because it was difficult to calculate, but because it was impossible to picture. And I have always believed that if you cannot picture something, you do not yet truly understand it. The question is this: does light actually move? I know what you are thinking. You are thinking, Monsieur de Broglie, this is absurd. We measure the speed of light. We have measured it with tremendous precision. 300 million meters per second. Every physicist knows this number. Einstein built his entire theory of special relativity upon it. How can I stand before you and suggest that light does not move? Patience, my friends. Patience, because I am not speaking carelessly. I am speaking from the mathematics itself. And the mathematics, if you follow it honestly, leads you somewhere very strange indeed. Let me begin where all things in modern physics must begin, with Einstein. In 1905, Einstein gave us two postulates. The first, that the laws of physics are the same for all observers moving at constant velocity. The second, that the speed of light in a vacuum is constant, always the same, regardless of the motion of the source or the observer. Now, this second postulate was revolutionary. Before Einstein, we assumed that speeds added together simply. If I throw a ball from a moving train, the ball travels at the speed of my throw plus the speed of the train. This is Galilean relativity. It is intuitive. It is what we experience every day. But light does not obey this rule. You can chase light at any speed you choose, even at 99% the speed of light itself, and still when you measure the light moving away from you, it moves at exactly the same speed, 300 million meters per second, not more, not less, always the same. This is the strange gift that Einstein gave us, and most people, when they hear this, simply accept it as a curiosity of nature and move on. But I could not move on, because this fact, this stubborn, beautiful, maddening fact, carries within it a secret that most people have never been told. Let me show you what I mean. When Einstein worked out the consequences of these two postulates, he derived the Lorentz transformations. These are the equations that tell you how time and space change when you move from one reference frame to another. And within these transformations, there is a term, a factor that appears again and again, which we call the Lorentz factor, or gamma. Gamma is equal to 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. Now, for ordinary objects, for you and me, for trains, for rockets, this factor is very close to 1. Our velocities are so small compared to the speed of light that the correction is tiny, almost negligible. But as the velocity approaches the speed of light, something extraordinary happens. The Lorentz factor does not approach 2 or 10 or 100. It approaches infinity. This is not an approximation. This is exact. At the speed of light, gamma becomes infinite. And what does this mean physically? It means that time dilation becomes infinite. A clock traveling at the speed of light, if such a thing were possible, would be measured by any outside observer to have stopped. Completely stopped. No time would pass for it at all. It means that length contraction becomes infinite. An object traveling at the speed of light, again if possible, would be measured to have zero length in the direction of motion. It would be compressed to nothing. It means that the relativistic mass, the resistance to acceleration, which would become infinite. You could push on such an object with all the energy in the universe and it would not accelerate further. Now here is the question I want you to sit with. Here is the question that kept me awake at night as a young man. If you were a photon, if you were a particle of light, and if we applied these same transformations to your situation, what would you experience? Of course, this is a delicate question. Einstein himself warned that you cannot naively apply reference frame transformations to a photon, because a photon has no rest frame. There is no frame of reference in which light is at rest. This is actually built into the second postulate. And yet the mathematics speaks to us nonetheless. From the perspective of any outside observer, a photon travels from one point to another in some measurable time. We can say light travels from the sun to the earth in approximately 8 minutes. This is a perfectly valid statement in our reference frame, in the reference frame of the earth, of the solar system. But now consider the space-time interval. This is a concept that goes deeper than either space or time alone. Hermann Minkowski, my fellow physicist, showed us that space and time are not separate stages on which physics is performed. They are woven together into a single fabric, space-time, and within this fabric there is a quantity called the space-time interval, which is invariant. It does not change from one observer to another. It is the same for everyone. The space-time interval between two events is calculated as the speed of light squared, multiplied by the time between the events, all squared, minus the spatial distance between the events, also squared. This combination, this particular mixture of space and time, is preserved across all reference frames. It is the one thing that all observers agree upon. And now I will tell you something remarkable. For light, for a photon traveling between two events, this space-time interval is always exactly zero. Think about what this means. The time component and the space component are equal. They cancel. For a photon, the space-time distance between its emission and its absorption is nothing, zero. The photon that left the sun 8 minutes ago in our reference frame and arrived at your eye just now, that photon, from the perspective of the space-time geometry, never traveled any distance at all. The beginning and the end of its journey are, in the geometry of space-time, the same point. My friends, I want you to appreciate how radical this is. We say that light travels. We say it moves through space. We measure its speed with extraordinary precision. And yet the geometry, the deep geometry of the universe, the geometry that Einstein and Minkowski revealed, tells us that the photon's emission and absorption are separated by no space-time distance whatsoever. Is this movement? Is this travel? I put the question to you honestly. I do not pretend to have a final answer that will satisfy everyone, but I want you to see that the word moves, this seemingly simple word, becomes deeply problematic when we apply it to light. Now let me come at this from another direction. Let me speak about my own contribution to this story, because it is directly relevant. In the early 1920s, I was wrestling with a question that seemed, to many of my colleagues, quite mad. Einstein had shown in 1905 that light, which everyone had taken to be a wave, following Maxwell's equations beautifully, behaved in some circumstances like a particle. He used this to explain the photoelectric effect. A photon is a discrete packet of energy, proportional to its frequency. So light, which is a wave, is also a particle. This was strange enough. But then I asked, why should this be a privilege of light alone? If a wave can be a particle, can a particle be a wave? I propose that every particle of matter, every electron, every proton, everything with mass and momentum has an associated wavelength. The de Broglie wavelength, as it came to be called, is simply Planck's constant divided by the particle's momentum. The smaller the momentum, the longer the wavelength. The larger the momentum, the shorter the wavelength. This was confirmed brilliantly by Davison and Germer when they showed that electrons passing through a crystal lattice produce diffraction patterns, exactly as waves would. My hypothesis was correct. Matter is wave-like. For this, I received the Nobel Prize in 1929, and I am grateful. But what matters to me here is not the prize. What matters is what this says about the nature of light. Because light occupies a very special position in this picture. Light has no rest mass, zero. A photon at rest does not exist. The very concept is meaningless. A photon exists only in motion, only at the speed of light. The moment you imagine stopping a photon, it vanishes, it ceases to be. For every massive particle, for the electron, the proton, the neutron, there is a rest state. There is a reference frame in which the particle is at rest, and we can study it in peace. But for the photon, there is no such frame. The photon is not moving at the speed of light, the way a car moves down a road at 100 kilometers per hour. The photon does not have a rest state from which it was accelerated to this speed. The speed of light is not something the photon does. It is something the photon is. This distinction, I believe, is crucial. We use the language of motion because motion is what we know. Motion is what we see. Motion is the vocabulary our minds were built with, living here in the slow, massive world of everyday experience. But the photon does not belong to this world. It belongs to the boundary of space-time itself, where our vocabulary begins to fail. Let me speak now about what happens inside an atom, because this brings us still deeper into the mystery. When an electron in an atom drops from a higher energy level to a lower energy level, it emits a photon. The energy of that photon is exactly equal to the difference in energy between the two levels. This is one of the triumphs of quantum mechanics. We can calculate the spectrum of hydrogen, every line, every color, with breathtaking precision. But notice what happens here. The electron is in a high energy state. It transitions and a photon appears. Where was the photon before? It was nowhere. It did not exist. It was not sitting inside the atom waiting to be released. The photon is created at the moment of emission, and it is destroyed, annihilated at the moment of absorption. The photon does not travel from a place where it was to a place where it will be. The photon is a transaction between an emission event and an absorption event. It is a connection, a bridge across space-time. And as I told you, this bridge has zero length in the geometry of space-time. The physicist John Cramer developed an interpretation of quantum mechanics, the transactional interpretation, in which this picture becomes very explicit. An emission event sends out what he calls an offer wave, and an absorption event sends back a confirmation wave. The photon is the transaction that results from this handshake. The exchange is instantaneous in the sense that the space-time interval is zero. Beginning and end are the same. I do not insist that Cramer's interpretation is the correct one. These matters of interpretation remain genuinely open. But I mention it because it illustrates how seriously physicists have wrestled with this very question. The question I am raising today is not a philosophical game. It is a real question with real implications that real physicists have dedicated careers to exploring. Now, some of you may be thinking, but de Broglie, we see light traveling. We see the sunrise. We watch the beam of a flashlight cross a dark room. Surely this is motion. Yes, from our perspective, from the perspective of any massive observer embedded in space-time, light appears to travel. We assign it a velocity. We measure that velocity. The velocity is real in every practical sense. When engineers build a GPS satellite system, they must account for the finite speed of light and for relativistic corrections, or the system will not work. The speed of light is not a fiction. But I want you to hold two things at once. I want you to hold the practical reality. Light has a speed, and that speed matters enormously for physics and for technology, and at the same time hold the deeper geometric truth that the photon itself in the full space-time picture does not experience a journey. For the photon, there is no duration, there is no distance. The emission and the absorption are one single event in the geometry of the universe. We see the journey because we are not the photon. We are massive, slow creatures, anchored in a reference frame where time flows and distances are real. We watch the photon cross the room and we say, ah, it moved, but we are describing our experience of the photon, not the photon's experience of itself. Can we even speak of a photon's experience? This is where physics meets philosophy, and I will not pretend the boundary is sharp. But I will say this, in the language of geometry, in the language of the invariant space-time interval, there is a precise mathematical sense in which the photon's beginning and end are not separated. And that is not philosophy. That is the mathematics. I want to connect this now to something even more fundamental, to the very nature of time itself. Einstein showed us that time is not absolute. It is not the universal river that Newton imagined, flowing at the same rate everywhere. Time is relative. It dilates. It slows. For a particle moving very fast, time passes more slowly as measured by a stationary observer. This is not an illusion. It is not a measurement artifact. It is real. Moons, unstable particles created in the upper atmosphere by cosmic rays, travel so fast that their decay is dramatically slowed. They survive long enough to reach the surface of the Earth. Without time dilation, they would decay high in the atmosphere, and we would never detect them at sea level. We detect them. Time dilation is real. Now follow this to its logical conclusion for light. If time dilation increases with speed, and if the speed of light is the absolute limit, then at the speed of light, time dilation is complete, total. A photon does not age. It has no internal clock. Between its creation and its destruction, no time passes for it whatsoever. And if no time passes, if the interval from birth to death is literally zero duration, in what sense did the photon travel? Travel implies a journey. A journey implies a beginning and an end separated in time. But for the photon, beginning and end are not separated in time. They are, in the only frame-independent sense we have, simultaneous. I find this extraordinary. I have found it extraordinary since I first encountered these ideas as a student, and I find it extraordinary still. The universe has built into it this remarkable category of entity, the photon, which carries energy and momentum across what we perceive as space and time, and yet which in itself has no experience of either space or time. It is the messenger that never travels, the bridge with no length. There is one more thing I want to say, and it concerns the wave nature of light. Light is electromagnetic radiation. It is oscillating electric and magnetic fields propagating together. Maxwell described this with 4 elegant equations in the 1860s, and the wave picture of light is immensely powerful. Interference, diffraction, polarization, all of these phenomena flow naturally from Maxwell's equations. The wave picture works. But here is the peculiarity. A wave is by definition something that oscillates over space and over time. A wave has crests and troughs, and they are spread out. They exist at different locations. They exist at different moments. When we speak of a photon, a single quantum of light, we are not speaking of an infinitely extended wave. We are speaking of something localized, something that can be detected at a single point, at a single moment, triggering a single click in a detector. And yet this same photon interferes with itself as if it were a wave extended across space. This wave-particle duality, which I helped establish for matter as well as for light, means that our classical concepts are simply insufficient. The photon is not fully captured by the word wave, and it is not fully captured by the word particle. It is something for which we do not yet have an adequate word, because our words were built from classical experience, and the photon is not classical. So when I ask, does light move? I am partly asking whether our classical vocabulary is adequate to describe what light is, and my answer is, it is not. The word move belongs to classical physics. It implies an object with a definite position, changing that position over time. Quantum mechanics has taught us that photons do not have definite positions until they are measured. They do not travel along definite paths. Special relativity has taught us that the very distinction between space and time, which underlies our concept of motion, breaks down for light in a profound way. Light does not move in any sense that would have satisfied Newton. Light is not a billiard ball crossing a table. Light is a phenomenon of the boundary, the absolute boundary of space-time. It is the universe's way of connecting events that, in the geometry of space-time, are not separated at all. When you look up at the night sky and you see the light of a distant star, a star perhaps thousands of light years away, perhaps a star that no longer even exists, you are receiving a message that, in the geometry of space-time, was never sent across any distance. The emission event and the absorption event, the moment the star's atoms produced that light and the moment your eye received it, are, in the only frame-independent measure we have, one and the same, separated by nothing. I think this should change how we look at the night sky. I think it should change how we think about the universe's capacity to be connected, to have its parts in communication with one another, joined across what we experience as vast and empty space. We are not merely receiving ancient signals from across the void. We are in contact, immediate, zero-interval contact, with events that our ordinary perception tells us are impossibly far away and impossibly long ago. The geometry says otherwise. I spent my life trying to understand matter and waves and the boundary between them. I proposed that matter has wave nature, and I was right. But light was always the more fundamental puzzle. It is not matter. It does not obey the same rules. It lives at the limit of what physics can describe, at the boundary where space and time themselves dissolve. Does light move? In your reference frame, in my reference frame, in every reference frame we can physically inhabit. Yes, it moves, and it moves at a constant, finite, measurable speed. This is real and important, and you should not forget it. But in the frame-independent language of space-time geometry, in the language that Einstein and Minkowski gave us, the language that asks not how far or how long, but what is the invariant interval, the answer is different. The photon's journey has zero length. Its duration is zero. The beginning and the end are the same point. And if the beginning and the end are the same point, my friends, then in what sense did it travel at all? I leave you with this question, not because I enjoy being difficult, but because I believe that sitting with this question, really sitting with it, feeling the discomfort of it, refusing to look away, is what it means to take physics seriously. The universe is stranger than our intuitions. It has always been stranger, and the strangeness of light, this thing that carries all the information we have about the cosmos, that connects every eye to every star, that makes vision and science and life itself possible, this strangeness is not a problem to be quickly resolved. It is an invitation to think more deeply. Thank you.